Hey there, my name's Carter. Welcome to OChem Bites. My goal is to teach you OChem in short, easy to digest bites. Please like and subscribe if you'd like to keep learning organic chemistry anytime a new video is released. Plus, it also supports me and my channel. Today we're going to cover how to find electron configurations easily. This is Orbitals Part 4. Let's get into it. Previously we discussed how to use this simple chart to find the electron configuration based on all the combinations of quantum numbers that are possible for each principal quantum number n. If this doesn't make sense, make sure to take a look at our previous videos in this Orbitals series. There's a full playlist. It's organized really nicely. Just as a refresher, let's find the electron configuration for nitrogen, which has an atomic number of 7. An atomic number of 7 means that we have 7 protons and 7 electrons that we need to put into their orbitals. So, reading from left to right and going down this chart, we start at 1s. The s orbitals can have 2 electrons max. So, we can put 2 of those 7 electrons from nitrogen over here. So, the first 2 electrons go to 1s2. Next, we have the 2s orbital. And again, the s orbital can have 2 electrons. So again, we can put another 2 electrons from this group of 7 into the 2s. Okay, so far we've accounted for 4 electrons, and we still have another 3 more electrons to go. So the next thing in this diagram is the 2p. The p orbitals can hold up to 6 electrons. So we can put the remaining 3 electrons into that p orbital. What does this all mean? This means the electron configuration for nitrogen is 1s2, 2s2, 2p3. And these numbers, the 2 electrons come from the green, these 2 electrons come from the orange, and these 3 electrons come from the red in this diagram. Using that diagram is pretty nice and easy, but there are even easier ways to come up with the electron configuration. The periodic table actually does this for us. Here you can see what information is buried in the periodic table. To get the electron configuration for hydrogen, you just start at the top left. It's 1s1. Helium is here on the top right, 1s2. Here's magnesium. It has an atomic number of 12, and its electron configuration is 1s2, so you look at this row, 2s2, so you're looking at this row, 2p6, and 3s2. So all we're doing is just reading from left to right, and you have to keep in mind how many max electrons each orbital can have. As we've previously stated, S can have a maximum of 2 electrons, P can have 6, D can have 10, and F can have 14. One thing to note is that for each row here, for S and P, you're representing a higher quantum number n. So this first row is n equals 1. This second row is n equals 2. Here is n equals 3. But now look at this transition. Even though here n equals 4, and both the s and the p have 4s in front of them, the d's have 3. And this is because of the limits on those quantum numbers that we've discussed in previous lectures. Alright, let's try another example without the cheat sheet from the previous drawing of the periodic table. Can you figure out the electron configuration for arsenic? So let's start at the top. 1s2, right? Hydrogen used to have 1s1, helium has 1s2. Next row, we have 2s2, 2p6. Here's a 2s2, here's a 2p6. Then the next row, 3s2, 3p6. Okay. Here, we've got 4s2. And remember what the quirk was with the d orbitals? They're n-1. So all of this is accounted as 3d10. And then we only have another 3 electrons remaining, and that is 4p3. Pretty cool, right? So for arsenic, the total electron configuration is 1s2, that's the first row, 2s2, now we fill the s orbital for principal number n equals 2, 2p6, now we're out here, 3s2, we've completed this, 3p6, okay, this is done, 4s2, that's these two, 3d10, that's all of this, including scandium. And then finally, those last 3 electrons are 4p3. That's the full electron configuration for arsenic. Let's just do another example. Let's do sulfur here, which has an atomic number 16. That means we've got 16 electrons that we have to place in different locations. So starting at the top, 1s2. That takes into consideration everything up till this helium. This is 2s2. That's all the way to beryllium. 2p6. That's all the way to neon. 3s2. All the way to magnesium. And then we just have a remaining 4 electrons here. That makes it 3p4. Doesn't the periodic table make it pretty easy? That's why this is a shortcut. So the full electron configuration for sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. Here's another shorthand. You could write the entire electron configuration for sulfur, or you could just use the last noble gas as a starting point. We do that because the noble gases, which are in this column, are extremely stable and have complete sets of electrons. As an example, take a look at helium here. Helium has 1s2 as the electron configuration. It has a full s orbital. Neon here has 2p6. It's a full p orbital. Argon has 3p6 completed. So everything here is very stable. So the shorthand for sulfur could just be neon plus 3s2, that's these two, and then 3p4, which are these 4 elements. And here's how you represent it. Neon, 3s2, 3p4. Another configuration you might see is an electron configuration chart like this one. While it's not a shorthand, it is a really cool way to represent electrons because you can use this to see the spin of electrons and what energy levels they are in. As you go up this figure, you have higher energy electrons because they're further and further away from the nucleus. In general, higher energy electrons are easier to steal in chemical reactions. Let's put sulfur in here just so that you can see what this configuration chart looks like. It's not much different from what you've already learned. The only thing you need to do is to draw in the spin of electrons with arrows. It doesn't matter which spin you draw first into a box as long as the 2 electrons have opposite spins. This is because the s quantum number, which can be plus half or minus 1/2, exists. So for sulfur, which has 16 electrons to fill in, let's draw in all the electrons into this figure. So starting at the bottom, we've got 1s2. See, we've got 2 electrons, one facing up, one facing down. We still have another 14 electrons to go. Here's another 2, 2s2. Okay, we've taken care of 4 electrons, we still have 12 to go. Here's another 6. Pretty cool, right? So far, we've taken care of 10 electrons. 1s2, 2s2, 2p6. We still have another 6 to go. Here's another 2. They go into the 3s orbital. And then we have another 4 remaining. 1, 2, 3, 4. So the full electron configuration for sulfur is 1s2, as you can see here, 2s2, 2p6, that accounts for 10 electrons. Another 2 go into the 3s2 orbital. That is now a total of 12 electrons. And then we have another 4, which make it complete 16. What you can see here is all the spins of the electrons, plus you can see this p orbital is completely unfilled. It only has 4 of the 6 electrons that it needs to be filled. So sulfur is 2 away from its nearest noble gas, which is argon. And that's it for this OChem Byte. Make sure you go back and check the other orbital videos in this series if you have any questions, such as what are orbitals, or why do I even need to know the electron configuration? And make sure you like and subscribe to keep learning organic chemistry in bite-sized chunks. Talk to you next time. Bye.